So welcome back. We're going to get started, and we are at 10:47. And let me understand. Scout using high-level design constraints to automatically generate design variations. Take it away, please.
Hi, I'm Amanda, and I'll be presenting Scout today. So many of you have tried to design an interface before, and you know that it can be really hard to make that interface usable and visually appealing. And one way that design can be improved is by creating variations. So work in the HCI community has shown that when designers create alternatives, it helps them compare the trade-offs between designs, and it leads to designs that are more usable and visually appealing. However, the designers don't always create many alternatives because it can be difficult to think of a completely new idea. Also, it can be time-consuming to manually create these variations by hand. And it can be hard for newer designers to follow usability and visual design principles with every variation that they create. So I'll introduce Scout, and it's kind of centered around the following questions. One is, can we generate good design variations automatically to help designers? And the other is, can we help designers follow design principles? So the system takes two inputs from the designer. One is a set of high-level design constraints. Example of this is something like the title text should be prominent, and that's so it is the first thing that the user sees when they look at this design. And then Scout takes the set of interface elements the designer wants to put into their UI, and then produces a set of design variations that satisfy the constraints. And the Scout system will also know about basic design and graphic design principles so that designs it creates are visually appealing. So the high-level workflow of this system that we're working on building is that it starts with this set of high-level constraints, like the title text should be prominent. Using the Scout interface, designers will define these constraints and feed those into those will go into our design synthesis engine, which will produce a set of design variations. And the designer will also be able to give feedback on the designs through high-level feedback constraints. And then Scout will respond with a new set of designs that satisfy their constraints. And they'll kind of be able to change these high-level constraints and give feedback continually until they narrow down the set of designs to the ones that they like. So now I'll give a detailed example of a high-level design constraint and how that will work in our system. And I'll be able to talk about the rest later during the poster presentation. So the structure principle states that interfaces should be organized in a way that is clear and intuitive for users, and related things should be placed together, unrelated things should be separated. So this is an example where this principle is not well followed. So the title and the tagline are completely separate locations, so it's unclear what the tagline is describing. So, and then here's a good example. So here the title and the tagline text appear together. So the user is more likely to see them as a cohesive unit in the design. So in Scout, the designer can create a high-level semantic grouping constraint, and that is used to group together related elements in the UI. So, and then it can have two aspects. One is order, which means the designer can fix the order of the elements or state that the elements are free to move in our variations. And type means that all of the sub-elements or inside of the group should be laid out uniformly. And that's kind of like a list or grid where all the cells need to be laid out in the same way. So then you have, so for an example, you have, say the designer has a group with order unimportant. They've grouped together some elements. And Scout will generate several design variations where it can change the position, order, and size of elements in the group. But it will always keep those elements together in the variations so that they are placed to be a visually distinct group in the overall hierarchy. A designer can also interact with the system through feedback constraints on the generated designs, and those can be element-specific things like keep this element here. They can be relational, like the subtitle should always appear underneath the tagline. Or they can be global, like use the 10-pixel layout grid to lay out the elements on. And then the feedback constraints are these high-level constraints, and they can be updated at any time to help the designer expand or narrow down the set of potential designs. So now I'll talk about the strategies we've explored so far in building the design synthesis part of this project, and especially looking for feedback on how we can improve some of these techniques. So we have 3 goals for this, this design synthesis problem. One is to be able to encode the high-level design constraints and basic design constraints, such as no 2 shapes should be overlapping, and feedback constraints that I showed you as a set of constraints to generate the designs. We also want to generate good designs that are respecting usability and graphic design principles. And those are things like alignment and balance and symmetry. And then we want to generate many designs quickly to make the system interactive so the designer can be interacting with this in real time. So we return to our inputs and outputs. And our goal was to produce the set of design variations that satisfy the constraints. Scout will know about basic design principles like preventing element overlap, also high-level constraints like the semantic groups, prominence levels for elements, and the feedback constraints. And then we have a set of design variables that are also encoded into the system that can modify different properties of the design to create the variations. And then for each design, for all of the elements, we produce x, y coordinates and height and width. So this means we're only currently producing layout variations, but we might consider doing more properties like fonts and colors in the future. We're kind of just focusing on the layout part for now. And then so kind of some more about how we're actually implementing this right now. We're using Z3 to encode some of these things into basic design, some of these constraints into a constraint solver. So we have the basic design constraints, we have the high-level constraints like semantic grouping, prominence levels, feedback. And then in addition to these encodings, we have a set of variables of design principles that we want to modify. So these are things like alignment and margin, label position, arrangement. So we're going to be kind of iterating through these things to make the different variations. And all of these have to be encoded into the solver as well. That's the approach we're currently taking. And then what we want to do is get a diverse set of designs. So right now we're using a random variable ordering when we do this search process. And then we use a backtracking and branch and bound to kind of assign the variables iteratively. And then we check and discard invalid solutions during this process and kind of assign the variables until we get a design, and then we keep doing this until we generate as many designs as we need, maybe 10 to 100, but it's kind of bounded on how many a designer can look at a particular point in time. So we don't have a need to generate thousands, of course. So now that we can generate solutions, how will we find the ones that are good? Well, so we have some visual cost variables. We will compute on these designs, like the amount of balance and symmetry, alignment, and white space. And we're kind of encoding all of these into a cost function that can rate each of these designs and give them an overall visual cost score. And then we have, then we generate the variations and then rank them by cost and return the lowest ones first. However, this leads to a kind of a challenge where it's really hard to get enough variations interactively, so enough of these good designs actually appear, because many combinations of these designs are not still not visually appealing. So we're exploring ways we can kind of modify the search order to choose the best combinations first, or something like that, to be able to help us to get better designs interactively. Another challenge is we want to give the designer a wide range of variations, and those we want to be spatially different because we want the designer to perceive them as different and covering a wide range of these different design variables. So right now we're kind of using a random variable ordering, and we're also thinking about computing a spatial distance metric on some of these designs to get variations, which seems to work okay, but we're kind of always open to any suggestions. And then we also want to make the system scalable and interactive. So we can't encode too many complex sets of constraints into our system, so that it kind of slows it down. So that's another big challenge in this project. So that's all I'll talk about today. But this project is currently a work in progress. So we're welcoming any feedback that can improve the direction of our design synthesis or the high-level constraints or anything else. So thank you.
Thank you.
Any questions, Ben?
So can you say roughly what fraction of the designs you generate are actually considered good?
So we haven't actually done any measurement on that. We're kind of just generating them right now. So, but I think in like what I'm looking at so far, it's maybe like a third of them that are actually like looking aligned. But I don't have any. Haven't actually done any informal measurement on this yet.
Can you imagine crowdsourcing the designs to see what people think, and then like building a ranking function using labeled data?
Oh, based on. No, I actually hadn't thought of that, but that seems like it would be a really interesting idea to take like feedback from other crowdsourcing or other people or other designers to rank it. I guess that would be it.
Pavel?
So one of the inputs to your technique is the set of high-level design guidelines.
Mm-hmm.
And I assume right now you're having experts write those or gathering them from the literature. Mm-hmm. But have you thought at all about attempting to synthesize those guidelines by looking at examples of good design already on the internet?
No, I actually hadn't thought of that either, so it's a great new idea. Yeah, I actually think I could maybe... yeah, right now we're just kind of like reading papers and looking at design principles and talking to designers and trying to synthesize a list based on all of this prior knowledge. But
the latest version of PowerPoint has, it doesn't have Clippy anymore, but you put stuff in and it rearranges your pictures. Yeah. Well, it doesn't rearrange. It shows you the preview, the designs.
Yeah, I've seen that. Yeah.
It's cool. Surprisingly effective.
It's cool.
And there was a lot of thought given to that. I'm interested to know how they actually did it, which I don't know. I think we're going to have to move on to the next talk. Julien, right, is giving that. Let's thank the speaker again. Thank you, Amanda. So Julien is going to talk about platform independent migration of stateful JavaScript IoT applications. Sweet.
Okay. Hello, everyone. So my name is Julien. So I'm working in collaboration with Kumseok, Jung, and Dr. Karthik Pattabiraman, faculty at UBC. So we're from the Department of Electrical and Computer Engineering. So the title of my talk is Platform Independent Migration of Stateful JavaScript IoT Applications. So I think I'm not going to surprise anyone if I'm telling you that the world of IoT is growing at a very, very rapid pace. Traditionally, the most traditional model of IoT, there were typically sensors and actuators. Sensors would collect some data. Actuators would, let's say, regulate some physical parameters. But most of the processing would take place in the cloud. So sensors would collect data, send it to the cloud for processing, and then the cloud would send back the results to the actuators. Now there's an emerging trend, the trend of edge computing, which allows for running applications on the devices themselves. So if you do edge computing, you can basically run more complex tasks, benefit from the power of the devices themselves that they can offer, and you can use these collective devices to run more complex tasks on them. So this is the framework of our research. So we've been proposing, well, we started this project about 1.5 years ago. It's called Things.js. So Things.js is a framework for developing and deploying high-level applications on IoT devices. So we want to be able to do edge computing. So we chose JavaScript, believe it or not. So we developers write code in JavaScript, And then our framework manages the execution of these JavaScript high-level applications on the devices themselves. So you're probably wondering why JavaScript. I'm also wondering the same thing. There's quite a few advantages. As you know, programmers are typically more productive in higher-level languages. So because you can abstract lower-level details, JavaScript also has a very strong user base. I think according to some surveys, Stack Overflow and some other indexes, it's ranking the first language. And there's this whole thing about the Web of Things. So with the Web of Things, you have JavaScript across the whole stack, client-side JavaScript, you have server-side JavaScript, and then with the Web of Things, the IoT interacts with basically the devices. So there is a logical fit of using JavaScript in that context as well. And in fact, there has been a few JavaScript virtual machines that have been proposed for the IoT, several VMs. Node.js has been adapted to run on some IoT devices. And even Microsoft, the Chakra Core engine, which is used in Microsoft Edge, can apparently run in some. We haven't tested yet, but it can run on ARM architectures, and we would like to test it. It can run on IoT devices, apparently. So there's really a big push towards running JavaScript on these devices. So let me give you a motivational example of why we would like to do edge computing. Let's suppose we are in this Microsoft building. There's probably a set of video cameras, a few different places. Let's suppose you want to be able to do motion detection to detect potential intrusions. Then in a classical scenario, you would have perhaps a set of cameras feeding, let's say, the frames to, let's say, the cloud or a cloud-like environment for central processing. But with an edge context, we can tap into the power that these devices will offer to offload the computations to these devices. So if we take our motion detection application, we would be able to perhaps have the video camera send their stream of images to a local device, to any device among all the IoT devices, let's say, in the building, to be able to run the motion detection task. So when I'm saying device, it can be any device. It doesn't have to be a device of the same kind. It could be a smart fridge that's in the building. It could be, someone mentioned, a smart toaster earlier. Why not? If it has enough computing power, we could potentially run the computations on this device. So this is what Things.js, our framework, provides. It allows us to execute, to schedule the execution, and to manage the execution of our JavaScript applications on these devices. But it might happen that a given device is not suitable anymore to run a given applications. So these things can change. These devices are still relatively low powered, especially a Raspberry Pi Zero. If a given device goes on battery power, it might be better to switch the execution of the task to a different device, or if the device is running low on resources, or in the case of motion detection, if you want to be able to process the motion detection at a higher frame rate, it might be necessary to migrate the execution to a new device. So this is what Things Migrate provides. Things Migrate is a sub-project of Things.js, the main component of this presentation. It aims at providing a framework for dynamically migrating JavaScript applications between devices in the edge, but not only devices in the edge, but in the cloud edge. So with Things Migrate, we can basically migrate dynamically applications between the cloud and the edge. So of course, we're not only limited to motion detection, but we can run any arbitrary JavaScript task on these devices, and Things Migrate can take care of migrating the task in real time. And the good thing about Things Migrate is that it does not require programmers to write specific code to handle saving the state and restoring the state. So with Things Migrate, any arbitrary JavaScript application can be interrupted at any point or almost any point during its execution. And then we can simply capture the state, send the state to a new device, and resume the execution at the state where the application was running at that moment. So we can do this between heterogeneous devices in the edge and in the cloud. So we're not limited to only one type of device. In fact, we can do cross migrations between different devices, between different OS platforms as well, and also between different JavaScript virtual machines. Right now, we only tested using Node.js, but we would support the migration between different VMs, and we want to be able to test that in the future. We tested with different versions of nodes across different devices. It was working. So just to, I don't have that much time to go into too much specifics, but just to give an idea of what challenges we need to implement to make our solution work, because we want to provide this full heterogeneity support. We cannot rely easily on solutions like modifying the JavaScript virtual machine to allow migration, because it would hinder compatibility between devices and platforms. So we must provide migration at the user level through user level code. But there's many challenges in doing that. I'm just going to expose some of the challenges that we face. A main challenge is that it's very difficult to capture the state of a JavaScript application because JavaScript has support for closures. And in closures, basically, functions can be used to trap elements of state. So if we look at this simple JavaScript function, it's simply a counter. It holds the value of the counter, and it returns a function that allows for incrementing the counter. So when you create a new instance of the counter, it keeps tracks of the value that's trapped inside the counter function. So because of the closure mechanism in JavaScript, there's no API to access dynamically the state of the closures in JavaScript. So we need to provide a solution to this problem. There's also first-class support for timers, and especially in the IoT in JavaScript, you want to be able to do some things at a regular interval, so we need to migrate the state of timers as well. JavaScript has a very specific and interesting prototypal model, so we need to take that into consideration given that the chain of prototype might change during its execution, so we need to be able to track that as well. And then there's also, the JavaScript is also asynchronous, single-threaded usually, so there's usually only one thread. So that means that we can only do migration at certain specific preemption points, or we must come up with techniques to allow the program to be preempted given that there's only one thread. So there's a wide range of challenges. So the solution that we propose, I'm not going to go too much into the specifics, but we have a code instrumentation approach. So that means that we instrument the original program to allow access at any time to the internal states of the various closures and the various elements of the application to be able to capture its state in a JSON format, send the state to the next device, and resume the execution exactly where it left off. So we have an open source project, so we encourage you to check it out. We did a full implementation of our system. Our results, we did some tests on the Raspberry Pi devices, 2 models of Raspberry Pi, plus 1 cloud-like server. We run a couple benchmarks. The overheads are quite high in our first version. The CPU overhead is about 30%. This is not too bad, but we're really working actively on bringing these numbers down. The memory overheads are more significant because we basically make a duplication of the data items with our approach, but we're working on alleviating these overheads as well too. Of course, there's always going to be an overhead because due to the nature of our approach, we modify we augment the JavaScript code, but we're trying to minimize these overheads as much as possible. We also support multiple migrations transparently. So I'm going to take maybe the 1 minute that I have to do a very quick demo. So I have this Ubuntu virtual machine. I don't have the devices with me because I didn't want to take the risk of bringing them across the border. But I'm going to basically here launch the motion detection on one virtual device. I have 3 virtual devices in my Ubuntu virtual machine. So we should be able to observe. OK, I don't think it worked properly. I know there were some network restrictions with the ports. I had to hack something, but I think there's a little network issue, so I might have to skip that part. But if you want to come and see me later, I can run a little demo for you if you want. So I think that's pretty much it. So please feel free to have a look at our GitHub page or resources. So thank you.
Thank you, Julien. Thank you. Any questions? Is Mark Maron here?
Yeah, I have a question. I'll ask later, but I'll ask now. So there's been a lot of discussion in the Node community, particularly about startup times with, serverless Azure functions, AWS Lambda, where I have a very large JavaScript application. I want to start it up, respond to a request quickly. But starting it up dominates everything else. It seems like what you're talking about here would apply directly to that situation as well, right? Rather than migration, I could use this for cold start.
You mean like the time to start the JavaScript virtual machine?
Yeah.
Yeah.
So is there any reason I can't serialize this to some file and inflate from that?
Yeah. In our case, when we do the migration, we migrate in like virtual machines that are already running on the devices, so we might be able to save some time on the startup.
Okay.
I don't know if that truly answers your question.
A little bit. It's something that's very interesting, seems very related. It would be great to chat about later today.
Yeah, sure. Yeah, definitely. Yeah.
Super. Other questions? Yes.
So there was all this work in like the 90s on like OS level process migration. Why is the language? Why isn't OS level migration an appropriate solution for the IoT problem?
We kind of excluded that solution because we have many different types of IoT devices. There's many different platforms, software environment, OSs. If you're in the cloud, it's mostly similar machines, so you might be able to make it work. But in the IoT, there's so much heterogeneity that it would be problematic, we think, yeah.
Okay, so the JavaScript level is the level at which everything is the same and you can get away with.
Yeah, so if everything's running on a JavaScript VM, we can migrate between the JavaScript VMs, yeah.
Okay, great. Thanks again, Julien. Very good. So Renato is going to tell us about compiling distributed systems, specifications into implementations. Please take it away.
Good morning, everybody. Thank you for the introduction. I'm Renato. I'm going to be talking to you about Pigo. And Pigo is a research project that we have at the Network System and Security Lab at UBC. So this is somewhat related to the talk that we had before the break. So we are also trying to combine formal verification methods into the field of distributed systems. So to start off with some motivation, so distributed systems are pretty hard to both design and build. And that one of the reasons for that is that you have an inherently non-deterministic sequence of events. And so one execution of your system, it has a certain ordering of your events, and then the next might have a different one, which is dependent on the state of your network, the nodes of your system. So it's dependent on a host of factors. And components can fail at any moment. So due to this reason, it's very hard to reason about your system, and it's very hard to think of how your system is going to behave under all these different conditions and all these different scenarios. But despite these difficulties, they're widely deployed, and when they fail, you can failures can sort of can impact other systems. So there have been reports of, for example, Amazon Web Services failures in that component cause failures for other companies, and then as a result, you could have a loss of millions of dollars. So the takeaway here is that we need a better way to build reliable systems. We need a way to properly reason about our systems in all these different scenarios. So there has been a number of approaches to this problem, and in particular trying to use formal verification tools into the field of distributed systems, and I'm going to briefly talk about a couple of them. So Fogarty, I'm sure a couple of you are familiar or have worked on it. It reduces the proof burden by you don't have to reason about failure state. You assume a lossless network, and Verdi produces a system that is fault tolerant. So, but you still have to write proofs. Ironfleet is a framework that allows you to match a specification with an implementation, and it makes it easier for you to prove that they're equivalent, but you still need to write both. And finally, Modus takes a different approach where instead of having you write a specification, you just model check the implementation itself. But then as a consequence, the state space is a lot larger because an implementation has a lot more details than a specification. So the model checker has to be a lot smarter, and there has been a lot of work on top of that. So the conclusion here is that these approaches are either hard to scale to large systems, in the case of checking an implementation, or they require a lot of work from the developer. So you have to write a proof, or you have to write some form of equivalence. So the approach that we take on Pigo is that, so this is sort of the workflow. So a developer writes a specification, which is abstract and high level, and we're using TLA Plus for that. Then Pigo takes care of compiling that specification into a matching implementation, and our target is the Go programming language. And the result is a verified distributed system. And the matching, the verification part here is that a specification is model checked with TLC, which is a model checker for the TLA Plus language, and Pigo generates the verified distributed system. So the advantage here is that this transition from a design level where you have a specification to the implementation is automated. So previously, you would have a developer do this transition, this translation for you. and then you could introduce errors, but then by automating that, you can get rid of this chance of adding errors. So to illustrate this workflow, I'm going to use it as an example this very simple system, which is sort of a round-robin resource sharing. So let's say we have n processes, and they make use of a shared resource. And they make use of this resource in such a way that each process uses it, and then the next one uses it up until the last process, and then it starts over. So we want to make sure that our system has this property where each process can use the shared resource in its own turn. So we can write a +call spec for that, and +call is specification language built on top of TLA+. So we can define a couple of constants here, which is the number of processes and the number of iterations where I'm going to use my shared resource. This is just a bit of syntax of +call. I'm naming this algorithm like round robin, and I'm simplifying my shared resource here by using a counter. So I'm just using a counter as an example of a shared resource. And then I'm declaring all my processes, and then what each process is going to do is that it's going to wait for the token to be equal to my own ID. So each process gets an ID. So as soon as I get the token, I'm going to increment a counter, which in this case, you're like simulating they're making some use of a shared resource. I'm going to be passing the token to the next process, and then finally I'm going to reiterate. So this is a very simple example, which illustrates like how a process can make use of a certain shared resource, and then the next one can make use of it, and then you have this kind of loop. So we can write a couple of properties about this very simple system. So one invariant that you could write is that our token is always within bounds. So in this case, our token is always between 0 and the number of processes -1 because they're 0 indexed. And we can also write a couple of properties. So one of them is that the counter converges. So the counter is your shared resource. So you could say that upon termination, when all processes are done, your counter is going to be equal to the number of processes times the number of iterations, and that all processes get the token. So this is a temporal formula, and you're saying that for all process that you defined, eventually the token equals to the process identifier. So you're saying that eventually every process is going to get a chance to run. So once you write that, you can model check your specification with TLC, and then TLC is the model checker. So this is the output that I get by running this example system. It checks that there are no errors, and then my properties hold. So I feel more confident that my system works as expected. The next step in this workflow is to actually compile this specification into a matching implementation. And a number of difficulties arise in this process, and I'm going to be talking about the most important ones. So for example, this variable counter here, it has a global scope in +call, so we need to make sure that a matching implementation also can access the shared resource. All processes can access this shared resource. So the way that we handle this is that we have a runtime that manages state for you, and you can manage it in different ways. There's a bit of developer input to sort of configure how you manage state, but the runtime takes care of that for you. The next issue is that labels, which are the ones that are highlighted there, they are atomic, meaning that once you start executing the code within a label, that is an atomic step, so it's a step of your algorithm. So a matching implementation makes sure that that step is also atomic. And you have very high-level constructs such as await, which just gets a predicate and then only executes the rest of your block once the predicate is true. So you also translate that kind of check into implementation that actually checks that predicate and only continues when the predicate is true. And then finally, you can use the compiled code. And the way we use it is that by default, you can choose which +call process you want to run. So we map the specification names that you use into the implementation. And in the case of a distributed system, you can configure like network setup and stuff. So the current status of this project is that Pigo is currently able to compile both concurrent and distributed systems. So in the example that I showed you before, each process could either be like a node in a network, or it could be a thread in a concurrent process. We have support for multiple strategies to manage global state. So you could have very naive approaches where you have all the global state in a centralized server, or you could have it spreading in different nodes of your system. And finally, it is able to compile simple distributed applications, and we are working towards supporting a larger subset of +call and TLA+, so that we can actually compile larger specifications. So as I said, a work in progress is to support a larger subset of both +call and TLA+, and generate fault-tolerant distributed systems. So right now, we don't deal with failures, and that is one of the challenges that they're working on right now. And we want to make it easy for developers to change the generated code, because as soon as you start making changes to the code, then all your bets are off, because you're again open to introducing errors in the process. So we want to leverage the LA Plus module system to sort of have a well-defined boundary between generated code and handwritten code. And finally, some limitations. Specifications are very high level, and so it is not everything can be compiled efficiently. We may require annotations, and one example of this is for types. So both TLA Plus and +call are sort of untyped, and but our target language is typed, so we need to. For now, we require some input from the developer to annotate the types of variables. And finally, right now you need to trust both the Pigo compiler and the runtime in order to claim the correctness of the end system. So in conclusion, Pigo tries to bridge the gap between design and implementation by automating the translation from a specification to an implementation. And our final goal is to make writing verified distributed systems easier without having to write proofs or without requiring a lot of input from the developer. That's it. Thank you.
Great. Super. Any questions? Yes.
Are you just compiling the +cal, or do the TLA properties get used somehow in your compilation process?
Yeah, so you can have TLA plus expressions in +call, but we currently don't look at like the outside TLA plus definitions. So this is another example where we use annotations. So if you have like functions that are defined outside of +call, we require some annotations in order to compile them effectively.
Yeah, I mean, the general problem is very hard because, as Leslie says, TLA is designed to basically be math for people, to help people think.
Yep.
He didn't design it either for proof automation or implementation. So you've got set theory,
yep.
and there are dragons, many dragons there. So
yeah.
I just wonder about your choice there. I mean, do you really? Especially since you're looking at distributed systems. I mean, TLA can do so much more. I mean, TLA is math, so you can do anything in it. And that's sort of very nice for expressiveness, but for compiling, maybe you should think of a more restrictive language.
Yeah, so +call is sort of like, I think it's closer to a programming language than TLA plus would be, and that's sort of the reason why we chose +call. So yeah, definitely TLA plus is very abstract and you can model pretty much anything. But we try to limit a subset of +call to something where it sort of makes sense to generate an implementation. So yeah.
You might need to add some types, huh?
Yeah.
Okay. Any other questions? Okay. Thanks again.
Thank you.
So. Mike Ernst is talking for Renee. Yes?
Okay. Yeah.
Very good.
Okay, so thanks very much. Renee was the point person on this work, and he should be giving this talk, but he wasn't able to come. So you'll hear it from me. So this is a talk about methodology, but don't go to sleep. It's actually interesting. So let's introduce the problem of fault localization. Fault localization is magical automated debugging. The idea is it tells you what line of your code is buggy. It takes two inputs, a defective program, a program in which you've inserted a bug, and a test suite where some of the tests pass and some of the tests fail. Then you run the fault localization technique, and its output is a ranking of the statements, telling you this statement is unsuspicious, this statement is very suspicious. Ideally, the programmer just looks at the most suspicious statement, fixes the bug there, and you go on with the rest of your day. So how do you know whether a fault localization technique is any good? Well, typically, the way we evaluate a fault localization technique is we compare it to the known location of the defect. You started with a defective program, and for evaluation purposes, you need to know where the defect was. I mean, more commonly, you really want to compare, rather than comparing one technique in isolation, you want to compare two techniques to figure out which one is better than the others. Great. So that's how we evaluate fault localization. So there are two inputs to fault localization, the defective program and the test suite. And that means when we evaluate fault localization, we're going to have to provide it with defective programs and test suites in order to figure out whether it's doing a good job or not. So where do you get these things? Well, a common approach in previous work was to use artificial defects called mutants. The idea is you take a correct program and then you make a bunch of little changes, like you might change sum times n into sum plus n, on the theory that this makes the program wrong. So there are a bunch of advantages to this approach, and the two biggest ones are it's really easy to create lots of defects, and we'd like to evaluate our tools on lots. If you want to do an evaluation, you want to have lots of data so you can do statistics and so forth. And the other advantage is now that you've introduced these defects, these fake defects, you know exactly where they are. So you can tell if the fault localization worked. Everything good so far? This is how it was done in the past. So we decided to do this a little differently. The first thing we did is we actually created a bunch of artificial faults, just like everyone else did, to replicate that work. We created about 3,000 of them, which is more than all previous studies combined. Then the next thing we did was we said, OK, are artificial faults any good? Well, the only way to figure that out is to have real defects. So we found real defects from version control systems that had been fixed by developers, committed into the version control history. We had 5 times as many of these as all previous studies combined. This took several person years to collect. And it's all publicly available in a data set called Defects4J. Defects4J stands for Database of Existing Faults to Enable Controlled Testing Studies for Java. So a bunch of people have proposed many, many fault localization techniques. Here are the 7 most popular ones. And then a bunch of people have evaluated those in a dozen papers. I mean, here's a funny coincidence. Oftentimes when people propose one, they find theirs is better than all the others. That's probably a coincidence, though. So here's what people have, here's what past studies have reported in terms of which one is better than the others. So we said, OK, let's replicate that previous work using a single unified infrastructure and careful statistics. And here's what we found. We found that we were able to replicate 7 of the 10 in terms of which technique was better. But of those, only 3 actually had a meaningful effect. So in other words, only 3 of these 10 results should ever have been reported. Somehow 3 of them are just the opposite of what we got when we tried it. And the others, they either didn't do the statistics or there was some other difference in an experimental setup. OK, so that's on artificial faults. But you're not going to be running your fault localization tool on artificial faults. You're going to be running on real faults. So let's take a look at real faults. We replicated all the experiments for real faults. Here's what we got. 0 out of 10 of the results replicate. They're either wrong, we got the opposite result, or we found that it was statistically insignificant. So in other words, you can argue with the methodology of previous results, but what we know is that definitely artificial fault, how fault localization techniques behave on artificial faults is not the same as the way they behave on real faults. So we also then looked, as I've said, people have proposed many fault localization techniques. There were 7 of them. I've put those in this space. We figured out what the design space of that was and actually evaluated 156 different techniques. And we found that none of those design decisions mattered at all. The first technique that was proposed 15 years ago is still the best on real faults. The others are actually better on artificial faults because that's what they did their evaluations on. We also, because it's what you do, we invented a new technique. We found it outperforms all other techniques on this particular metric that actually matters, because no one's going to look at all the output, just look at the little top bit of the output. OK, so coming back to evaluating fault localization, we now have a new standard methodology. Where do we get these defective programs from? Well, you should use real defects from a data set like Defects4J. These are mined from the version control history. They're real problems that were really fixed. Now we need to figure out where to get these test suites from. Luckily, because you're using this Defects4J data set, it provides real tests. These are real tests that were written by developers. They were committed with the fix. Again, we're using a real artifact, not fake artifacts. This sounds fantastic, right? No, you should all be screaming in terror at this point. This is awful. Because I just said they're committed with the fix. When were those written? Were those written after the person had figured out what the fix was and had an understanding of the bug? Well, when you actually run fault localization, you're going to be running it on a user-submitted bug report from an issue tracker, not on some idealized test that the developer created after the fact. Uh-oh. So we took a look at the difference between user-provided tests that are from issue trackers and developer-provided tests that are committed with the fix. We found that developer-provided tests, there are more tests, they have more lines of test code, they have less coverage though, and that's because they're more focused on the particular parts that are defective. More coverage of the defective, less coverage overall, but more coverage of the defective code. They have more assertions in them, and those assertions are stronger, using an objective, not subjective measure. Okay, so tools have to run on tests. Do tools behave differently if you run them on developer-provided tests, like everyone has done so far, or user-provided tests? So here are two particular tools. One's fault localization, one's automated program repair. For fault localization, for all the metrics that people use, they perform better when they're when they're run on developer-provided tests than when they're run on user-provided tests. Another downstream tool you might care about is automated program repair. So we chose these programs. Automated tools were able to correctly repair 5 out of 100 defects using developer-provided tests. When we used user-provided tests instead, they were only able to repair 1 out of 100 defects. And that particular one actually happened to be such a good test that the developers accepted it without change. Overall, making a comparison, when you're using developer-provided tests, when you're using user-provided tests, which is how you're really going to use this, there were fewer generated patches. This is the main metric people use, but who cares how many patches it generates? You care which ones are correct. There are far fewer of those. We can see that here. And the tools run much longer than reported. And part of this problem is that fault localization is an important subroutine used by automated program repair, but it's about the program repair too. Okay, so now we know the right way to evaluate fault localization, or at least we think we do. That says you should be using you shouldn't be using artificial defects like mutants. You should be using real defects. And you shouldn't be using the developer-provided tests that are written with too much knowledge. You should be starting from what's actually going to be available. Now, this talk is not about fault localization. Fault localization is interesting, but it's really about research. So the right way to evaluate any research is exactly the same, right? The first is you need to focus on results, not ideas. Ideas are a dime a dozen. Most ideas actually turn out to be wrong. You need to evaluate them and actually provide value to the scientific community. That means you need to evaluate your tools using realistic artifacts. You need to evaluate them in an end-user context. If you don't want to do these things, you're maybe doing interesting theory, and that's super cool, but you don't care about programming and programmers. So here I've been beating up on fault localization research, but I could have given this same talk about any number of other topics in programming languages, in machine learning, elsewhere. I don't think fault localization is any worse than any other research. It's actually better than many of them because that community cares about these things. I mean, in some sense, that community has found its conscience, and what the purpose of this talk is to ask you to help out all those other areas that are still seeking that same conscience. So please go out and do that. Thank you very much.
Questions?
So one challenge is gathering that real-world data. Could you comment on why it was so difficult to collect 300 real bugs?
Okay, great, good question. So why was it so hard to find 300 real bugs? I mean, there's 300 real bugs in my software any day. And the reason is that the goal was for each one of those defects to be real, committed to a version control system, cross-linked to an issue tracker with a bug report in it, and the test suite had to pass beforehand. The test suite had to fail afterward. Sorry, the test suite afterward had to fail before the fix. The test suite had to succeed after the fix. This is not true of bugs in general, by the way. And then there was an important and difficult manual step, which is when people commit a bug fix, they also choose this as a great opportunity to do a few refactorings or maybe add a feature in there. And so we manually minimized all those so that the only differences are actually the bug fix. Because if you want to evaluate, did this identify the right lines of code, you'd better know exactly which lines of code have to do with the defect and which are just other things that happen to be in that commit. And there's a bunch of tooling and other stuff that was built in that I haven't mentioned here, which is another reason it took so long to build that data set. Great question, though. I had swept that under the rug.
Question here.
So I think the work's totally fantastic. It's great. So one thing you just said was that almost all real bugs don't meet the criteria that you said, right? And so it seems to me like still the way that people are framing the fault localization research is they're trying to make something that's tractable that they can kind of work on. So they have all this signal, right, from the set up. But it still doesn't match the case with most bugs that people actually encounter. So do you have some recommendation or thoughts about this kind of framing of the research?
Yeah, so that's a great point. So, we took issue trackers. Those issue trackers had tens of thousands of bugs in them. We selected 300 or 400 of them. And these are ones that we could get to reproduce on our machines in a deterministic way and that had a test. And so there is a possible selection bias here. So I think a really interesting point of research is how do we automate some of that enormous, programmers hate to do stuff by hand. Anytime you're doing stuff by hand, you're trying to, you want to think about automating it. So those are things we're working on right now, is figuring out how to automate those things. It's a great research topic. If you want to help me, we're working hard and confused.
Another question here.
Yeah, so you weren't able to replicate anyone's fault localization results on real faults. That
Correct.
Seems like pretty strong evidence that mutation testing doesn't actually embody real bugs. Is that the takeaway from that?
No, there are two styles of fault localization, one that uses code coverage and one that uses mutation analysis. It turns out that in mutation analysis, we have reasons, we understand why these things don't replicate, and it turns out that mutation analysis is fantastic on artificial bugs and doesn't work at all on real bugs, because real bugs often have more than one character that's wrong and some other stuff like that. So there's actually evidence that mutation testing is highly effective, and there's also evidence that there are cheaper ways to get those same kinds of benefits. And I'm happy to talk about those offline.
Okay, we have a question.
But it's a great point.
Question back here.
Is it possible to use the real artifacts to improve the generation of mutation testing result?
So you're asking. So one thing we can do is we can use real artifacts to evaluate whether a particular approach is good. Are you asking something different?
I want to generate more tests so I can use machine learning.
Right. So why don't we take all this stuff and dump it into a machine learner, and it'll deeply produce a good result. So that sounds fantastic. Let's talk.
Another question here.
So you looked at the bugs that were in the defect tracker. What were the bugs that didn't make it to the defect tracker because they were caught by the test suite? So are those things that you want your technique to also incorporate?
Right. So tremendous selection bias here, right? It's defects4j is the best data set out there by a long shot, and it's just far from perfect. So another thing is we can only see stuff that actually got committed to the public repository and then reported later. In some sense, those are important ones because they're actually affecting the public perception of your problem. But it would be nice to also, the other ones are less bad, but it would be nice to handle those as well. We don't have data about those. Or rather, we have data, but it's all data from tracking developers on their computer and that kind of stuff. And so they're very limited in scope, those data sets.
Last question.
Is there a risk of overfitting a new tool to defect JS, and how would you recommend to avoid that?
Okay, so there's a question. We have this defects4j. What if there's a monoculture of evaluation where everyone just evaluates on this? So we have actually, since this work, added another about 35% new bugs to defects4j, and we redid our analysis and it didn't change. So that at least says that the results are stable. It doesn't say whether some new tool that was tuned to this would get overtuned. I don't have an answer for that. There are hold one out approaches you could use.
Okay, great. Thanks again, Mike.
Thanks very much.
Oh, wow, that was fast. So, Pavel, Casuius verifying web pages. Please take it away.
That's right. OK, so it's great to be here. And for the next 10 minutes, I'll be telling you about my work for the last 3 or so years, which if I had to summarize it in even less than 10 minutes, I would describe as applying programming languages and software engineering thinking and techniques to web pages. All right, we're done. OK, so I should maybe explain a little bit more. When we talk about web pages as programs, when I talk to people about it, people often assume that I'm talking about the server-side code. Maybe they think I'm going to be statically analyzing PHP. I am not. That sounds terrible. Or perhaps even worse, they think that I'm talking about client-side frameworks. I am also not statically analyzing JavaScript. Instead, I'm talking about sort of an underappreciated aspect of dynamism in web pages, which is the front-end layout. And so this is looking at how HTML and CSS can be viewed as programs that respond to user inputs, produce outputs, and then verifying that those programs behave correctly. OK, so what do I mean by looking at HTML and CSS as a program? On the topic of verifying programs, I had an embedded video, but I think a moment ago it wasn't working. So instead, I'm going to do, let's call it a live demo, because what I wanted to show you was how websites react to change. And this is Google Slides. So I can just pop over to the real deal. This is healthcare.gov live. And you can see that though it looks like a static page, it actually responds to user inputs. Like, for example, the fact that I'm here shrinking the size of the browser window, and the page it is showing is changing. That's not the only input web pages take. I can also change my browser's preferred font size. And if I do this enough, you'll notice that up in the top right, the Go button has disappeared. Oh, sorry, the search button has disappeared. And that search bar itself has left its blue background tab. So this is a bug. They should probably fix it. It wasn't like this morning, but it definitely improves the talk. OK, so web pages are programs. They respond to user input. They provide output, which is the visual arrangement of elements on the page. And if we start thinking about these as programs, and we start recognizing that they have bugs, we immediately start wondering, how can we determine whether a web page layout is correct? OK, so I'm not talking about verifying full functional correctness. None of this work happens inside Coq or Lean or any of those theorem provers, because it's difficult to imagine how you'd write down the full specification for what a web page ought to look like. But that doesn't mean we can't easily write down formal properties that should be true of web pages. And here I'm talking about things like text shouldn't overlap, all the buttons should be on the screen so that you can actually click them, and the headings should maybe form a visual hierarchy. So these are common sense properties web pages should satisfy. But to put some further oomph behind these, they are also best practices for satisfying the Americans with Disabilities Act, which in the United States requires even private sector websites to be accessible to all Americans. And so not only are these specifications common sense that your website should satisfy, they also have a legal and a moral imperative behind satisfying them. So if we've got these important specifications, we got these programs that might not meet them, we want to find out if they do, the natural question is how we can verify that web pages satisfy specifications. And that's what I've been doing. And the challenge to doing that is that it is not immediately clear how to apply PL techniques to web pages. Fill in the blank. And so my work has mainly been in addressing 3 challenges that bridge the gap between how we think about web pages and how we verify programs in general. And so these 3 challenges are to write down a semantics for how web pages behave, to invent a logic in which we can describe visual properties, and then to find a way to reason about web pages compositionally, piece by piece. Now, I don't have that much time, but I will try to give you the main idea behind how each of these challenges were handled. And so the first one is writing down a semantics for web pages. And this, of course, means determining for a given web page, for a given set of browser parameters, size, font size, and even some of the obscure ones like how big are your OS scroll bars in pixels? For all of those parameters, determining what the web page will look like as a result across possible browsers and so on. So there's kind of 2 sources of truth for how web browsers work.
The first is the W3C English language standards. And the goal of these standards is to make sure all browsers behave the same. So they're informal, and in a lot of places they're ambiguous. For example, I recently learned that the CSS standard is incompatible with the existence of scroll bars. They're working to fix that in the new version. The other source of truth, which is maybe more realistic and in some sense the ultimate arbiter of truth, is the actual implementation of web browsers. So web browsers are executable. They actually do a thing for every web page. They are actually how web pages look. But there are several million lines of C++. Even the rendering engines themselves are long and complicated because they're written with performance in mind. And they've accumulated 23, I looked that up recently, 23 years since Netscape, 23 years of cruft in those rendering engines. So to derive a semantics for how web pages actually behave, we needed to combine the strengths of these two approaches. So from the standards language, what we actually took are conformance tests made by browsers, made by the standards body, and a few made by us. And on those conformance tests, we tried to match the behavior of existing web browsers. So between these two things, we were able to write down a semantics for how CSS behaves, how web browsers render web pages. And that describes the behavior of a lot of complex web pages and has the side benefit of significantly shrinking that standard. So we went from about 35 pages of text to about 1,000 lines of formalism. So that's how we wrote down a semantics of web pages. And that was published in OOPSLA a few years ago. Once we knew how web pages behave, the next step was figuring out how web pages should behave. So we needed a logic to write down properties that web pages should satisfy. So we wrote one. It looks like this. So here is a property that we've expressed in our logic. It says that for every box, so think of this as a rectangular element on your page. For every box, if that box is a button, then that rectangle should be entirely contained within the root box, so that's the browser window. In other words, all the buttons should be on the screen. And you can see here that this logic allows quantifying over the boxes on a web page. It allows querying properties of the HTML, so that's what's going to define what elements are boxes. And it also allows geometric predicates that talk about the final rendering of that page. So we've got a logic where you can do all of this. It works great. We can express 14 standard accessibility guidelines. These are the sorts of things that come up in, for example, Department of Justice guidance documents for how to satisfy the ADA. And we've also ensured that not only is the logic expressive, it also compiles to decidable queries. And what that means is that we can take a web page and we can ask Z3, are there any reasonable browser sizes, font sizes, scroll bar widths, and whatever else weird parameters we've got, under which your web page does not satisfy the specification you've written down. OK, so that's how we made a logic for visual properties, and that'll be published at this year's PLDI. So if you're there, come to the talk. It'll be great. It'll be like this, but longer. And the final step is between the first 2 points, we have a tool that you can give a web page and ask, are there any rendering parameters, we call them, under which your web page does not satisfy this specification? But that's not really how web pages are written. They're not written as one monolithic blob. You work on pieces, and those pieces can be reused between pages, and then the page is also edited over time. So we wanted a way to take a web page that you might want to verify and break it up into pieces, each of which you can reason about independently, prove properties about separately, and then put that back together into a whole page property that you want to prove. So we call each of these pieces components, and you can not only break them up once, but you can do this recursively, so you can have nested components. And so we've done that. We've built a verification engine that can handle not only full web pages, but components of web pages, and reason about the context in which those pages appear. So for example, to prove this property, which I showed one section earlier, can you believe it was a minute and a half ago? Instead, you can prove a property like this. We've broken the page into components, and for each component, if that component itself is on screen, then all the buttons in that component should be on screen. So we've now turned that original spec that I've written into a spec that only does per component reasoning with preconditions on those components that allow us to capture the effect of the rest of the web page. And so we've got a tool that does this. It allows you to reuse reasoning because each component can appear on multiple versions of a web page, can appear on multiple pages on a website, or even in some cases across websites where you're reusing libraries like the Twitter Bootstrap. And it's also much faster because you're verifying much smaller components of web pages, and you're gaining significantly because you can reason about each of these components in parallel. So that's the 3 challenges we had to meet, and our tool Casuius meets all 3 of those. Please check us out, and I'm happy to take questions.
Thank you. Questions? Yes, Karthik.
I know you said at the beginning you were not dealing with verifying JavaScript code, but a lot of web pages execute JavaScript code in the beginning to set things up. How do you handle those, or do you plan to handle?
Did you see the slides beforehand? Because it turns out there's secret backup slides, which discuss sort of the future work that we would like to do. And that's reasoning across this client-server divide. Yeah, I'm not kidding you. I had these prepared. So this talk covered that layout portion, and what you're asking is whether we can extend it in the future to cover all 3 of those components. And I do think we've got some of the technologies built out that could eventually lead to that. What we'd really like to do is to take these components that you're reasoning about and replace part of those components with variables and generate additional side conditions on those variables that we can then trace through the JavaScript or PHP or Python or whatever code that is filling in those variables. So we'd like to do that in the future. We haven't done it yet, but it sounds like a great idea, and I'm excited about it. Other questions? I don't have more backup slides, don't worry.
So I used to work at Mozilla, and the interesting thing about, so you took the conformance tests and boiled it down to semantics. You were talking about taking those tests from or the pages of text from W3C, but what WG specs were actually reverse engineered from the browsers as well in the first place. So you're boiling down the what WG stuff further, I guess. Are you feeding your stuff back to the browsers or the spec committees is what I'm asking.
So
the browser vendors really would love to have better versions of formal model that they should be implementing that is a superset of what they have already implemented, but cleaner.
Right. So you're asking whether we've fed our semantics, which are in some sense cleaner and, I mean, not saner, but at least better specified, back into the browser. We've talked to a few people at browsers. Especially interesting to them is verifying incremental rendering. So that's not something we've worked at, but something a formal spec could be really useful for.
Okay.
So we've sort of just had preliminary conversations with them.
Have you talked to the server team?
We've talked to a few people on the server team, but not maybe as intensely as we should have. I'd be happy to talk to you afterward if you can put us in touch more.
So, in theory, could you give Casuius to the Department of Justice and run it on like the entire web of the United States, and then like sue a bunch of people and fine them?
It's actually even better than that. This goes into a few legal subtleties, but we could run it on the internet and sue all of those people and collect damages. It's sort of a legal experiment embedded in the ADA that has proved very effective at making people enforce it. So that's definitely an idea we've considered. And if you've got sort of a law firm you could hook us up to, we'd love to fund our research in this particular fashion. Yeah.
Okay, with that, let's thank the speaker. Okay, so just to remind you of the schedule, I really hope outside there, where breakfast used to be, there's some lunch. I think we have box lunches. And we're going to reconvene back here in a half hour. So please get your box lunch. You can mill around here to eat. You can go not too far away. I know it is sunny outside, but you didn't hear it from me. And please be back here at 12:30 when we're going to hear from Jonathan Protsenko about Project Everest, Theory Meets Reality. Ben, did you want to?
Just a couple things. The 2 rows of chairs, 2 or 3, I guess, rows of chairs, we're going to move those out to make room, more room for the posters. If you haven't put your poster up, maybe try to do that over lunch because the poster session, I think, starts at 2. So we want to set that up. And in terms of the lunches, we do have lunches for a vegetarian option. If you didn't ask for a vegetarian option, probably don't prefer those lunches, at least until a number of people have had a chance to do that. So with that, I guess we're ready for lunch. Yeah. Any other?